to start with some examples from the 1000 Genomes Project. Jeff discussed this a little bit. The paper came out yesterday. If you haven't read it, I encourage you to do so. It was released under a Creative Commons, no commercial use, share-alike license, which I think is the first time nature has ever done that. So you can take the paper and give it to anyone you want. And that's the license that nature has given us. The goal here was to create a catalog of human variation, and it's about shared variation. Jeff mentioned this. So this is variation that occurs in the population and is less concerned about variation that is specific to an individual. And the strategy for doing this is low coverage over many samples. So back when the project was originally conceived, the plan was to do about 1,000 samples at about 2x coverage. And the plan was to take about 3 years to do that. As it turned out, technology increased dramatically, and we also discovered that, in fact, 2x coverage was not the ideal kind of sweet spot to find the information. It turns out to be between 4 and maybe 8x coverage on population sizes around 400. And so the main part of the project is built onto that assumption of subpopulations or different populations around the world of 4 to 500 at 4 to maybe 6x coverage. So of course, the pilot project has done a lot of work to evaluate and pioneer methods for sequence analysis and variation discovery. It seems very, very simple to do variation discovery in resequenced genomes, but in fact, it's actually very difficult to do it at high accuracy. If you just think about it, one could get all the variants in a genome right to 99% accuracy by just saying there aren't any. And so to go through carefully and find out where the variants are is a big challenge, and to get them all right. So I discussed a little bit about our original plan, which was developed in September 2007. Of course, the whole reason that this plan came about was because sequencing costs had dropped dramatically from the days of Sanger sequencing. And so the plan was about 6 terabases of sequence. It was going to take about 3 years to generate it. Well, so in reality, by the time we started generating data in the first part of 2008, we'd produced 4 terabases in about 6 months. And the dramatic reductions in sequencing costs continued. And in fact, in some ways, they accelerated. At the same time, many more samples became available. So the limitation on the 1000 Genomes Project, which is now up to about 2,500 samples hoped for by the end of 2012, the limitation is not the sequencing capacity. The limitation is the collection of these samples and their transformation into lymphoblastoid cell lines, which are used in the project. So there were 3 pilot projects. Again, Jeff mentioned these, to deep sequence 2 trios. That's not going to be part of the main project. And then the low coverage sequencing to evaluate the methods of using low coverage data for population variation discovery. It's important to note that basically all of the data that's reported on in the paper that came out yesterday was generated in 2008. And so it's not tremendously representative of the type of data that's now available from the Illumina GA2s or from the HiSeq machines. The reads are much longer, you get much more data from them, and in fact the data quality is much higher in many cases. So what this means is that some of the methods that were developed in the pilot project to in some ways cope with the data that as it existed in 2008 aren't quite as necessary today as they were back then. So you may have noticed that there's companion papers available in Science and also in Genome Research. There's a whole host of other companion papers in progress. And the full project data collection and analysis are underway. So this is just a couple of figures from the paper. This is about SNP discovery. There was about 15 million SNPs identified in the pilot project. Most of the SNPs, of course, most of the common SNPs had already been seen. But of the novel SNPs, as one would expect, 84% of these were in a single population, and only 4% of the novel SNPs, being defined as not in dbSNP build 129, were found in all of the populations. So I mentioned already the difficulty in getting accurate variant calls from resequencing data. The false discovery rate for the SNPs in the 1000 Genome Project was set at about 5% for the SNPs and about 10% for the small indels. Not surprisingly, genome-wide SNP distributions vary. You see high variation rate in places that one might expect, including the HLA region on chromosome 6, as well as most of the telomeres. There's also notably low variation in certain places, One of the places is the relatively highly conserved region on 3p21. Jeff showed this, or a similar slide to this already, about the value of additional samples for variant discovery in a low coverage method. And essentially what it means is by the time you get to 220 low coverage individuals, you end up with about 99% of the synonymous variants. And by the time you have 320 low coverage individuals, you end up with about 98.5% of the non-synonymous ones. So the pilot project, again, only covered 180 samples. These were from the HapMap populations. The extension, which is ongoing now, to about 1,100 samples, I think we're at 1,044 samples currently at greater than 10 gigabases of sequencing coverage. Includes additional European populations as well as African, East Asian, and admixed American populations. So the data is available. Anyone can download it. A lot of people do. We just recently ran the stats, and something like, between the two FTP sites, something like 3 petabytes of data have been downloaded in 2010. So on the 1000genomes.org site, we have regular news about the project. It's about 90 terabytes to download the entire data set if you want it from one of these sites. Now, of course, it's mostly in data formats that we invented in the project. And so if you're not in the project, you've maybe never heard of them or haven't used them before. So this is something of a challenge, but they were kind of designed for good reasons. But we also have tried to make this data as accessible as possible to as many people as possible. People who are just interested in a single gene and are not interested in 90 terabytes of data. So we built a browser for the data. It's built on the Ensemble platform. We update this about every 2 months as more data comes out of the project. I really think we have to solve this. We have to solve these details of being able to make the variant data that we know is out there accessible as soon as we can. We know that when data is subject to access controls, it's a burden to use. And it does limit the number of researchers that will reuse the data. The HapMap data has been reused by thousands of researchers, tens of thousands almost certainly. Something like 1,100 have applied for access to the Wellcome Trust Case Control Consortium data sets, although they're incredibly valuable resources. Still, it's necessary, and so the policy and technology in this area are important. It's also important to remember that 5 years ago, accessing this type of data wasn't just difficult, it was impossible. And so to make it just really difficult is progress. And we need to make it continually less difficult over time. And it's important as well. So this was a commentary in Nature Medicine over the summer. It's important as well to keep in mind that the public is watching this. So this commentary has a headline, "The delay in sharing research data is costing lives." Now, in and of itself, this is quite an inflammatory headline. But if you read into the commentary, the statement that is made is, and I pulled it out, I'll read it here, is, "Making science work fast enough for patients will require researchers to treat information with greater urgency. Surely, if anyone knew that he or she possessed life-saving data, he or she would act swiftly to share it, just as an intelligence officer would rush to report evidence of an impending terrorist attack. When failing to share data becomes equivalent with preventing terrorism, there's a change taking place in the public thinking about how we produce and share research data that can impact human health in society. And so I think we have to keep our eyes on this. For those people who believe that data should be widely shared, in the end, this is a laudable goal. Methods such as this and these statements, they might be slightly more extreme than needed to get the goal done. We need to create the managed access databases. As I've mentioned, these are done, but they're not fully efficient. And then we need the ability to search for variant existence in these databases, and basically to present users with the result that says, yes, this variant exists, something's here, but you have to apply for access to actually see what it is. And finally, when the data is available, we need to be able to find it and to search for it. Obviously, you can't search for A or C or G or T in Google and get any response. So it has to be a well-ordered search mechanism.